This video will go through graphs and networks and look at some of the terminology that you'll need to have a really good command of in this unit. So what I've got here is just a lexicon, a group of definitions regarding networks, and I'll go through each of the definitions and then put them into practice in an example. So first things first, a network is a set of points, some or all of which are connected by a set of lines. And those points and lines have specific terms that are used to describe them. So let's move that. So this is an example of a network here. And the first thing I want to point out is this concept of a vertices or vertex. The first thing is that they are also known as nodes, so it's important to understand that the term vertex and node, or vertices and nodes, are often used interchangeably. So it's the name given to a set of points in a network. So A is a vertex, B is a vertex, C is a vertex, E, D, F. All of those are vertexes, or together are a set of vertices or nodes. What we've got in the next definition is an edge. And an edge allows undirected movement from one vertex to another. So you can see in this example here, we've got movement allowed between A and B, and that movement is undirected. Typically, they'll show you if movement is directed by putting an arrow on the edge, and that indicates that this is one-way movement. You can only go from A to B this way and B to A that way. And if it is directed, we call it an arc. Undirected movement, though, is an edge. The third, is it the third one? Yeah, third or fourth term I'd want to look at is a loop. That's an edge that starts and finishes at the same vertex. So this is an example of a loop here. And what we're basically saying is from vertex C, you can get back to vertex C by following this loop here. And because it's undirected, of course, you can go either way around that loop. Okay, the next term is this concept of a connected graph. And a connected graph is one where it's possible to travel from every vertex to every other vertex. And so clearly this example here is not a connected graph because there's no way of getting to vertex E. There's simply no edge that connects any of these vertices to vertex E. And so what we call vertex E is an isolated vertex. Okay, we could connect it up. That is a possibility. So we could connect that up. And we get to choose which way we want to connect that up. And I could connect E to D. I could connect E to A. I could do any number of things to connect that up. And that would then make it a connected graph. Okay, a path. The way of traveling from one vertex to another. So in this example here, I can draw a path that goes from point A to point F in a number of ways. I can go from A to B, B to C, C to E, E to D, D to F. That's one example of the path. We write down a path like this. So we start with the vertex we begin with, and then I simply write the order in which I visit the different vertices. So A to B to C, to E, to D, to G, to F. Okay, and we can draw another path as well. So if I select my pen again, let's do it in red this time. I can go A to B, B to C, C to D, D to F. So that path will be A to B to C to D to F. Okay, the final thing is the degree, the number of edges that join to a vertex. And it's a little bit confusing when it comes to loops, so I've chosen this example specifically because a loop counts as a degree of 2. I've got a way of working out the degree of a vertex. I actually just draw another circle around the vertex, and then I simply go around in a clockwise direction and count the number of lines that appear. First line, second line, third line, fourth line, fifth line, and sixth line. So this has a degree of 6. Okay, so it's got 5 edges that join to it, but the degree is actually 6. Okay, so it's important to understand that difference. Okay, so on to the examples from graphs and networks. So this is the first example I'd like to do here. So for the graph below, state the number of vertices. Well, that's easy. 1, 2, 3, 4, 5. There's 5 vertices. Okay, the number of edges. Got a simple system for doing that. Once you count an edge, you put a slash through it. So that's first edge, second edge, third edge, fourth, fifth, sixth, seventh, and eighth. There's 8 edges. Okay, the degree of each vertex. So we've just spoken about that. What I do, I'll write my working out down here. I've got C, D, and E. And let's just write the degree of each one. So A has a degree of 1, 2, 3, 4. B has a degree of 1, 2, 3. C has a degree of 1, 2, 3, 4, 5, 6. D has a degree of 3, and E has a degree of 0. Okay, the number of edges, again using the formula. So there's a simple formula to work out the number of edges. And what I do is I add together the number of vertices of a particular degree and then divide the result by 2. So what I can see is that there's 2 vertices of a degree 3. So I do 2 times 3. I add that to the number of vertices that have a degree of 4. That's 1 times 4. And I add that to the number of vertices that have a degree of 6. That's 1 vertice times 6. And I divide the result by 2. So 2 times 3 is 6, plus 4 plus 6 all over 2. I'll just scroll down a little. 6 plus 4 is 10, plus 6 is 16 over 2. And that, of course, equals 8. And that directly matches up with what I found in question B, which is by a manual count. I also found that the number of edges is 8. The last question asked whether the graph was connected or not, and of course it's not, because E is an isolated vertex. Example 2 is not too bad either. For the given network diagram above, determine whether the following paths exist, F, A, B. So to do that, I simply start at F, go to A, and go to B. That definitely exists because I can do or follow that route. FAD, let's try that. So I can go from F to A, but the problem is I can't get to D. There's no path actually connecting it. So this is not a path that exists. The final thing they'd like us to do here is to list 2 paths from vertex F to vertex C. So here's vertex F, and we want to get to vertex C, so I can go F, A, B, D, C, F, A, B, D, C. I could also do, let's try another one, F, D, C, F, D, C. There's many answers to this. In fact, probably an infinite amount of answers to this question here, but they're two very simple paths.